Okay, students, today we'll discuss about the magnetic field intensity at the axis of a circular loop. Let's speak about the magnetic field intensity at the axis of a circular loop, for which we are having a circular loop like this. You could see a circular loop like this, and this is the axis of the circular loop. For a real life situation, let's have a circular loop like this. Now, if this is our circular loop, means the line which is passing through the center of the ring perpendicular to ring is called axis. Therefore, this line is called as axis. That line is demonstrated as our red line. Okay. Therefore, you could imagine the tangent of this ring. Imagine the tangent of this ring. At this particular point, the tangent will be like this. At this particular point, tangent will be like this, like this, like this, like this, and it will change. Okay. Therefore, the tangent of the circular ring, you could imagine it. Then, if I'm taking the next diagram, you could see the red color axis of the ring, and next you could see many blue color lines. That is, you could see this line, this line, this line, and all. They are lines from the ring to the axial point. They are lines from the ring to the axial point. Okay. Therefore, let me hold the axis like this. Let this be our axis. And if we are taking the next blue color lines, let me use the blue color pen itself. Therefore, this is the blue color lines. Okay. Imagine that this is our circular ring, and in that circular ring, the pen that is passing through the center is the axis, and the blue color lines are the lines which are marked as R in our diagram. You can see a diagram in the screen, and the blue color lines are these lines. Can you imagine the angle between this blue color line, that is this pen, and the tangent of the ring? Can you imagine the angle between the blue color line and the tangent of the ring? Yes, as you have imagined, that angle is 90 degrees. At all situations, this blue color line and the tangent, it will make an angle of 90 degrees. Blue color line and the tangent will make an angle of 90 degree in all that situation. If you are taking the blue color line like this, then also the tangent and blue color line is making an angle of 90 degree. You have to imagine this. Okay, this is very important in this derivation. Now we have imagined that and all. Now we are going for the derivation. Let me take a fresh new page, and I'm going to draw a diagram. That is, look over here carefully. That is, I'm using red color. Yeah. Then this is the circular ring that we are considering in this situation. This portion is, or the portion which is drawn like this, it is outside the screen, and the dotted portion is inside the screen. Let's say the dotted portion is inside the screen, and the bold portion that is outside the screen. And the current passing through this loop is I. It is like this. This is the direction of current passing through the loop. Okay. This is the direction of current passing through the loop. And in this case, we have to mark DL, or we are going to find out the magnetic field intensity at the axis of the circular loop, for which let me draw the axis of the circular loop. It will be yeah, it will be like this. Okay, this is the axis of the circular loop that we are considering, and let this distance be x. The distance from center to the axial point, it is x. Okay, then we have to find out the magnetic field intensity at this particular point. For that, let's say the radius of the circular loop that we are considering is a. Normally we used to mark the radius as r, But in this situation, I am marking the radius of the circular loop as A. Okay. Then we will find out the magnetic field intensity over here by using our Biot-Savart's law. What's Biot-Savart's law? dB is equal to mu 0 by 4 pi I dl sine theta divided by r square. This is our Biot-Savart's law. Okay, this is our Biot-Savart's law. For using Biot-Savart's law, we have to mark a dl. We have to mark a dl. Therefore, dl is the small segment of the loop which is in the direction of current. Therefore, let's mark a dl at the extreme top portion. This is our dl. Okay. Therefore, dl's direction is in the direction of current. Therefore, I am marking this as our dl. But actually, the dl's direction is not like this, since the loop is perpendicular to the ring. Or screen perpendicular ആയിട്ടാണ് loop ഉള്ളത്. The loop is perpendicular to the screen. Therefore, the direction of dl, it's not like this. It is actually outwards. ഇവിടെ dl outwards ആണ്. The direction of dl ഇവിടെ outwards ആണ്. ആ dl ഇങ്ങനെ പോയി ഇവിടെ എത്തുമ്പോൾ dl inwards ആവും. അതുകൊണ്ട് the direction of dl in this case ഇവിടെയാണ് നമ്മൾ സ്മോൾ സെഗ്മെന്റ് എടുക്കുന്നതെങ്കിൽ ആ സ്മോൾ സെഗ്മെന്റ് ഡിഎലിന്റെ ഡയറക്ഷൻ ഇങ്ങനെയാണ്, അതായത് സ്ക്രീനിന് പുറത്തോട്ട്. Therefore, the direction of dl at this particular point, it is actually outwards. Normally we used to represent a dot mark for outwards. Therefore, this dot mark is for the direction of dl. Okay, remember that, that's important. dl's direction is outwards. Then what is r? R is the distance from dl to the point where the magnetic field intensity is to be measured. Therefore, let's mark r over here. The r, let me use blue color. This is our r, distance from dl to the point where magnetic field intensity is to be measured. Therefore, this is our r. Okay. Therefore, give me the angle between dl and r. The direction of dl, as I have mentioned, it is outwards, and r is a line like this. dl and r is making an angle of 90 degree. Therefore, why? It's because dl's direction will be tangentially outwards. This is r, and this r and dl is making an angle of 90 degree. Therefore, I could write dl is perpendicular to r, and the value of angle, it will be 90 degree. Since angle is 90 degree, we could write the db's expression as mu 0 by 4 pi I dl by r square. db's expression can be written as mu 0 by 4 pi I dl by r square, since sine 90 is 1. Okay. Therefore, now we are having db. Let's go back to this diagram. Now we have to mark the direction of db. The direction of db. Direction of db can be obtained by Biot-Savart's law in its vector form, that is db is equal to mu 0 by 4 pi I dl cross r divided by r cube. This was the Biot-Savart's law in its vector form. And if that is the Biot-Savart's law in its vector form, the direction of db will be in the direction of dl cross r. The direction of db will be in the direction of dl cross r. And if you have to mark the direction of dl cross r, you know the dl is outwards, r is in this direction. Then you will have to curl the right hand of your, or curl the right hand like this from dl to r. If you are curling your right hand like this from dl to r, then the thumb of your right hand will denote the direction of what? The thumb of your right hand will denote the direction of the db. That is, since dl is, or dl's direction is outward and r is like this, if you are curling your right hand from DL to R like this, the direction of DB in this particular point, it will be like this. It is perpendicular to R and DL. It is like this. Therefore, this is the direction of DB. Okay. Therefore, this is the direction of DB at this particular point. It's very important. You have to understand this. Okay. Then, in the similar manner, if you are having a DL at the extreme opposite end, if you are considering a DL over here, the direction is outwards. And if I am considering a DL at the lowest extreme point, if the DL is like this, actually the direction of DL, if the direction of DL over here is outwards, means in this region, the direction of DL is actually inwards. Inwards means the direction is made as a cross mark. Therefore, at the extreme lowest point, the direction of DL is inwards. That is, if I am demonstrating at this point, the direction of DL is outwards, means in this point, the direction of DL, it will become inwards. Okay, inwards. Okay, then you have to mark our R. R, what is R? R is the distance from DL to the point where the magnetic field intensity is to be measured. Therefore, the distance from DL to the point where the magnetic field intensity is to be measured. This is our lowermost R. This is our R. And for this DL, we have to mark the DB over here. At the lowermost point, the DL is inwards. R is like this. Therefore, for that DL, the R's direction will be, you have to use your right hand like this. You're seeing the mirror image. Therefore, I'll draw it. It will be the direction of R or the direction of DB. The direction of DB, it should be like this, means the direction of DB should be like this. This is the direction of DB. If you are curling your right hand from DL to R, the diagram will be somewhat like this. You should imagine it, or you could curl your right hand, and this is the direction of DB. Okay, the direction of DB will be like this. That means the direction of DB will be perpendicular to R. And let me use the red color over here. Therefore, due to the lower DL, the direction of DB, it is like this. Okay, DB. Then let me rub these hands. Then eraser. Now we know the direction of the DB due to the upper DL and the direction of DB due to the lower DL. We have to proceed further. Then for this, next, let me mark an angle. The angle between R and X, it is theta. If the angle between R and X is theta, this angle will also be theta. R and X, theta. Okay. Then now let's resolve this upper DB into two mutually perpendicular components. Let us resolve this upper DB into two mutually perpendicular components. That is, one component like this and one component like this. Okay. Then you just refer this line X. That X line is perpendicular to this vertical line. This X line is perpendicular to this vertical line. And now you could see this R. This R is perpendicular to DB. R is perpendicular to DB, X is perpendicular to vertical line. Therefore, I could say this angle is also theta. The angle between R and X will be exactly equal to the angle between the two perpendiculars of R and X. That is, this angle is theta. If this is DB and this angle is theta, you could say this is DB cos. It's not. Let me mark this angle as phi, this angle as phi, this angle as phi. Then I could mark it as DB cos phi. Okay. Therefore, this is DB sin phi. Why I am marking it as phi? It's because we have already named theta over here. Therefore, I'm using another name, that is phi. Okay. Therefore, phi dB sine phi, dB cos phi, and dB sine phi. In the similar manner, I could resolve this lower dB. I could resolve this lower dB. Pay your attention over here. Let me use another color. Let's use, yeah. Then the lower dB can also be resolved into two mutually perpendicular components like this. And this x line is perpendicular to this lower vertical line, and this r is perpendicular to dB. Therefore, I could say if this angle is phi, means I could say this angle is also phi. For that, you could write this is dB, means this is dB cos phi, and this is dB sin phi. Okay, dB cos phi and dB sin phi. From this diagram, it is clear that the dB cos phi components are in the opposite direction. Therefore, they will cancel out. The dB sin phi components are in the same direction. Therefore, the total magnetic field intensity in this case, should it be 2 times dB sin phi? No, it's not 2 times dB sin phi. It's because in this case, we have only taken these two dls. We could take dl at these 2 points. We could take dl at these 2 points. We could take dl at any side of this conductor. Okay, the conducting loop. And in all that case, if you're taking a dl over here and if you're taking a dl over here, their dB cos phi components will get cancelled. Similarly, if you're taking a dB over here and a dB over here, their dB cos phi components will get cancelled. Therefore, the total dB sin phi components will be the sin phi components of all these. Therefore, it's not 2 times dB sin phi. It is actually integral of dB sin phi. You will have to take all the dB sin phi components. That's the dB sin phi component of here, complete dB sin phi component. That's the reason why we are writing B is equal to integral of dB sin phi. Okay. Then let's substitute. We know the value of dB. The value of dB is actually mu 0 by 4 pi IDL by R square that we have obtained over here. Okay. Now we know the value of dB. Since we know the value of dB, let me write that dB over here. That is, we know since dB is equal to mu 0 by 4 pi IDL by R square. The value of dB is mu 0 by 4 pi IDL by R square. Okay, then we have to obtain the value of sine. It's not sine theta, it's actually sine phi. We have to obtain the value of sine phi. If we are obtaining the value of sine phi, we could substitute the value of dB and sine phi and we'll get the answer. Therefore, in order to obtain the value of sine phi, you concentrate on this right angle triangle. There's a right angle triangle over here with hypotenuse R, opposite side A and adjacent side X. If you're considering this right angle triangle with an angle phi, the hypotenuse is R, opposite side is A and adjacent side is X. What is sine phi then? Sine phi is opposite side by hypotenuse. Therefore, sine phi is A by R. You could clearly see the sine phi is A by R. Okay. Therefore, sine phi can be obtained as A by R. And now if we are substituting for B, B is equal to integral of what is dB? dB is mu 0 by 4 pi IDL by R square. And what is sine phi? Sine phi is A by R. Okay, then in this integration, we could take the constants out. Mu 0 by 4 pi, it's constant. Therefore, it's taken out. I, current passing through the loop is also a constant. It's taken out. A, the radius of the loop, it's also a constant. Therefore, it is also taken out. divided by r square into r, that is r cube. R cube also, r value is also numerically a constant. You could clearly see the r value is also a numerically a constant, therefore it's taken out. The only thing which is remaining inside the integration is integral of dl. What is dl? Dl is the small length of the loop. Therefore, if dl is the small length of the loop, integral of dl will be the total length of the loop. Integral of dl will be the total length of the loop. Total length of loop means, let me write integral of dl, it is the circumference of the loop. Therefore, is it 2 pi r or 2 pi a? Look at the diagram and say, is it 2 pi r or 2 pi a? It is 2 pi a. Since the radius of the loop is a in this situation, therefore integral of dl is circumference of the loop, that is 2 pi a. Then we could write mu 0 I a divided by 4 pi r cube. Instead of integral of dl, we will have to write 2 pi a. Then we could do the cancellation process, that is pi and pi will get cancelled and 4 and 2 will get cancelled and there will be 2 over here. Then ultimately, let me write it over here. We will get b is equal to mu 0 I a into a, it is a square divided by 2 r cube. We are getting an equation like this: b is equal to mu 0 I a square divided by 2 r cube. Okay, then if you are substituting for r, what is r? From this triangle, r is the longest side or hypotenuse. Therefore, we could write r is equal to root of a square plus x square. Root of a square plus x square means I could write a square plus x square whole to the power 1 by 2. R is root of a square plus x square or a square plus x square whole raised to 1 by 2. Therefore, what should be r cube? R cube should be the cube of this, that is a square plus x square whole raised to 1 by 2 whole cube means it is whole raised to 3 by 2. Is it clear? R cube is a square plus x square whole raised to 3 by 2. Okay. Therefore, we could say the b value can be rewritten as mu 0 I a square divided by 2 into r cube can be written as a square plus x square whole raised to 3 by 2. A square plus x square whole raised to 3 by 2. Hope you are understanding this. Mu 0 I a square divided by 2 into a square plus x square whole raised to 3 by 2. This is the magnetic field intensity at the axis of the circular loop. The expression for magnetic field intensity at the axis of the circular loop is B is equal to mu 0 I a square divided by 2 into a square plus x square whole raised to 3 by 2. What is A? A is the radius of the circular loop. What is I? I is the current passing through the loop. What is X? X is the distance from center to the axial point. The distance from center to the axial point. Okay. Then this is the magnetic field intensity at the axis of the circular loop. Now let's discuss some special cases. Let us discuss some special cases. Let me create some space over here to discuss the special cases. Okay. The first special case that we are going to discuss is the point is at a very large distance from the loop. That is, if the point is at a very large distance from the loop, if the point is at a very large distance, let's say this point is at a very large distance, means the value of x will be very large compared to a. Therefore, the first special case is if the point is at a very large distance, that is, I could write the value of x is much greater than a. If the value of x is much greater than a, we could say a square plus x square is approximately equal to x square. Since x is much greater, x square value will be very much greater and x square plus a square can be approximated to x square. Okay. Therefore, we could rewrite this equation as B is equal to mu 0 IA square, there is no change in the numerator, divided by 2 into a square plus x square whole raised to 3 by 2 should be written as x square raised to 3 by 2. X square raised to 3 by 2. What is x square raised to 3 by 2? 2 and 2 will get cancelled. Therefore, it is x cube. Therefore, ultimately, B is equal to mu 0 IA square divided by 2x cube. Mu 0 IA square divided by 2x cube. This is the formula that we have to take if the point is at a very large distance. Then let's discuss the second special case. The second special case is if the point is at the center of the loop. If the point is at the center of the loop, that is, in the second special case, we have to shift this point from here to here. That is, if you are shifting this point from here to here, the x value will get decreased, and finally the x value will become 0. Therefore, if the point is P is at center, if the P is at center, that is the point is at center, means the x value will become 0. If the x value is becoming 0, if the x value is becoming 0, it is clear that we could write a square plus x square as a square. It's not x square. A square plus x square can be written as a square. Okay. Then this equation will be rearranged as mu 0 IA square divided by 2 into a square raised to 3 by 2. That is a square raised to 3 by 2. It will become 2 and 2 will get cancelled and it will become a cube. A cube and this a square, there will be denominator a. B is equal to mu 0 I divided by 2a. A cube and there will be numerator a square and a cube will get cancelled and there will be an a in the denominator. Therefore, this is the formula that we will get if the point is at the center. Then as a third special case, let's say if there is n turns, the loop is having n turns, means on this diagram, the loop was having a single turn. But if the loop is of n turns, means we could say if loop is of n turns, if the loop is of n turns, means we could say the B value will be n times of this. N times of this means n mu 0 IA square divided by 2 into a square plus x square whole to the power 3 by 2. This should be the B value if the loop is of n turns. If the loop is of n turns, this is the B value that you should remember. Okay. Therefore, now we have discussed about the magnetic field intensity at the axis of a circular loop, and the answer for magnetic field intensity at the axis of the circular loop, it is B is equal to like this. And there are the special cases. If the point is at a very large distance, this is the formula that you have to remember. And if the point is at the center, this is the formula that we have to remember. And if the loop is of n turns, the formula that will be n mu 0 IA square divided by 2 into a square plus x square all raised to 3 by 2. Okay, you just practice this now itself. That is, once you have written this along with me, you will have to do this by your own and practice it. On practicing this, you should remember one thing. This dB, it's not the extension of this R. This dB, it is not the extension of this R. Actually, it is perpendicular to this R. This R is perpendicular to this dB. And this R is perpendicular to this dB. It's not the extension of this R, and this is not the extension of this R. Okay, this R is perpendicular to this dB, and this R is perpendicular to this dB. Okay, remember that. Hope you have understood this. We are stopping our video.